Work, energy, and power. The question is, why do we need this idea of work or energy or power when we already know Newton's laws and kinetics? And the answer is because Newton's laws and kinetics are kind of clunky to use in difficult situations. So let's take two situations we've already learned. I've got a ball moving at 10 meters per second, and it's going horizontally off a cliff, and it's going to come fall down from a height of 15 meters. And I want to know what the final velocity of this thing's going to be. So I know that my y velocity begins at 0, and I'm going to travel downward at 9.8 meters per second for 15 meters. So my final y velocity will be 17.1 meters per second. I know that I'm going to keep my initial 10 meters per second, so I can figure out my final velocity by saying 10 squared plus 17.1 squared, and I'm going to get 19.8 meters per second as my final velocity of that projectile. What if I take the same ball and I roll it down a 30-degree incline by starting at 10 meters per second? Well, I could draw myself a force diagram. I've got gravity, and I'm going to break gravity into two components, a normal component and a parallel component, or a downward component. And I'm going to have a normal force. So my normal force and the normal force of my gravity, normal component of my gravity, are going to cancel. And if I want to solve for the, downward force, I would say force down is equal to m times g times sine theta, or ma equals mg sine theta, which is going to give me an acceleration of half of gravity, or 4.9 meters per second squared. I know that the distance that I'm going to travel downward here is not 15 meters. It's actually longer than that because I make a triangle, and this is the hypotenuse of the triangle. So if I use a trig function, I can say that the distance is equal to my opposite side, which is 15, over my hypotenuse, which is the distance. So I can do this trig problem, and I can find out that my distance here is 30 meters downward. Okay, so I can use my formula VF squared equals VI squared, or 10 squared, plus 2 times my acceleration of 4.9 times my distance of 30 meters, and I get 19.8 meters per second. Coincidence? I think not. Actually, there's something going on here that is pretty universal, and if we can tap into it, we can start to avoid thinking about these problems in terms of their kinetics, and instead work in energy or work terms and see if we can make that a little bit easier. Okay, what about this situation? Let me slide this over here. I've got the same ball still moving at 10 meters per second, and it's going to go a total drop of 15 meters, but I'm going to do it at this incline and then that incline, and then go straight across, go up an incline, go straight across, go down an incline. What's my final velocity going to be? That's a lot of math. I need to do a whole bunch of trig here, find out parallel and perpendicular components for each section, and calculate the total distances of each one. This is a ton of work. So instead of doing that, we need another option. Sure, I could use Newton and kinematics, but if I'm asked this on a multiple choice question, can I do it in 90 seconds? No way. So I'm going to introduce this idea that's called energy. And energy is a property of an object that allows it to do work. And I'm going to give it the unit joule, or just J. It's named after a French physicist who did a lot of work with work, energy, and power. And we're going to take a look at what energy is and how it operates. Mr. Balsham has a really interesting way to intuit energy. So I'm going to show you a hammer that I have here. It's pretty big. Here's my hand. Gives you an idea of the size. It weighs about, 5-10 pounds. So maybe 2 to 5 kg. and it's sitting on the ground. And Mr. Balsha would ask you, like, are you afraid of this hammer? And the answer is probably no. It's a hammer sitting on the ground. What's the worst that could happen? I'd stub my toe on it. What about this person? Should this person be afraid of the hammer? Okay, so what about this person? You can catch, right? Okay, good. I thought you said you could catch. So I asked about a hammer, and I said, are you afraid of a hammer? And most people said no. But when I held it above someone's head, now there's something different about the hammer, right? There's that person underneath the hammer should be afraid. What about the person I threw the hammer at? Why should they be afraid of the hammer? What does the hammer have when it's above your head? Or what does the hammer have when I'm throwing it at you that it doesn't have when it's lying on the ground? Physicists call that energy. So there's a list of them that you probably know. One of them is called potential energy, and that is energy due to position. Now, a lot of people will take the common English definition of the word potential, and they'll say, oh, potential energy must be the energy that you're going to use in the future. Because if I say that you have a lot of potential, that means, well, you're not really good now, but in the future, you're going to be awesome. And that has nothing to do with physics. This is not an energy in the future. This is just an energy because of where you are. And we'll talk more about that in a minute. Kinetic energy is the energy due to your motion or your velocity. The Greek term kine, K-I-N-E, is like the root in kinematics, meaning like when we studied motion. You'll see it in the word cinema also, which is a moving picture. So this is energy of moving. We can lump them together and take our potential, U, and our kinetic energies, K, add them together, and that gets described as mechanical energy. So if a problem ever talks about mechanical energy, they mean the sum of your potential and your kinetic. This unit, we're also going to talk about elastic energies, which are the energies of a spring or a rubber band, and I'm going to abbreviate them like E-spring usually, or ESP. That's how we're going to get those. Energy is highly dependent upon your reference frame. Okay, so the energy of position, generally in this class, it's going to be how high up you are, right? And how high up you are depends on where we want to say the 0 point is. So if you are, like myself, sitting in a second floor bedroom, then how far is the floor below me? Is it about 3 feet below me? Or is it about 10 feet below me because I'm on the second floor? And actually, I could solve the problem either way by saying that the floor is just where my feet are, or the floor is where the ground is. And either way, I might get 2 different answers, but they're both equally okay. Okay? Same thing with velocity. Depending on where I am, I might disagree with you on how fast you're moving. Like right now, our classic example is, are we moving right now? And the answer is probably not. You're just sitting there watching this video. But from another reference frame, we are screaming around the sun as we orbit it. And so, sure, the energy that you report is going to depend on what reference frame you operate in. The interesting thing is that a change in energy is not dependent on your reference frame. So let's say that I believe that we are stationary right now, and I get up and I walk at 1 meter per second. Then I've had a change of 1 meter per second, right? If you believe that we are screaming around the sun at 1,000,000 meters per second, which is a little extreme, but let's say you were right, and then I get up and move at 1 meter per second, well, now I'm moving at 1,000,001 meter per second. My change is still 1 meter per second. So even though we disagree about what speeds I actually have, We will not disagree on what the change in that was. The same thing goes for energies. So we need to be careful about that. Okay, I want to introduce a new term called work. And work, as soon as my phone comes back into, there we go. Now we're back into focus. Work is going to be the change in energy. And in order for work to be done, I need a force to act over a distance. Now, this seems like a pretty simple definition that work is a change in energy, and we're actually in a kind of a loop because energy is the ability or the property of allowing yourself to do work. So we've gone in a big circle. What is work? That's when you change your energy. And what is energy? Well, that's when you do work. So we really haven't defined what this thing is. It's kind of a strange concept. I'm going to make it a little more awkward by saying that work is equal to force times distance, but this dot in between them is really important. In physics, there's actually two ways to multiply. One's called a dot product or a scalar product, and the other one's called a vector product. And we'll look at the vector product later this year. But today, the dot product is when I take two vectors, force and displacement, and I'm going to multiply them and get a scalar. My work is a scalar. So what this means is that I've taken two vectors, multiplied them to give me a scalar. And in order to do this, we have to set some rules. And the rule here is going to be that work is only done in the direction of the force. So what do I mean by that? So let's say I have a force going to the right, but my object is actually moving rightward and upward. So I've got some force F, and I've got some distance d or displacement d that I'm moving, but the whole displacement is not allowing me to do work. I only do work in the distance parallel to my force. So if I do some trig on that, I'm going to find out that work is equal to FD cosine theta. Because as we know from last unit, in order to find this side here, I'm going to have to use the trig function cosine. Now, if you memorize this, you're going to get yourself into trouble. Because is it always the case that we're going to use cosine theta? No way. The test designers will put you in situations where you might need to use sine of theta. So why does the equation generally get written as FD cosine theta? It's just a convention. I want to make sure that you always draw yourself a diagram and then you always analyze it in terms of making sure that the force and the distance that you use are parallel to one another. When I lift the hammer up, I have to apply an upward force to the hammer, and the distance or displacement also goes up. I'm doing work on the hammer because my force and my distance are both coming upward together. When I lower the hammer, I'm still applying an upward force, but now the distance is going down. Now you'd say, well, aren't I applying a downward force to make the hammer go down? No, I'm not. Gravity is, but I still need to apply an upward force. If I don't, the thing will fall. So I'm applying an upward force while the object moves downward. That actually gives me a negative work. We're going to talk about that soon. Now, the third combination that we could possibly have is if I take the hammer right here, I apply an upward force, but I move it sideways. So my force is upward, but the movement is sideways. Am I doing any work? And the answer is no. So if I held it here and I dropped it on someone's head, that would hurt, right? If I hold it here and I move it sideways and I drop it over here, does it hurt any more or any less? The answer is no. Like, right, I'm going to drop it on someone's head, it's going to hurt the same amount. So I haven't changed the energy of the object by moving sideways. The force was in one direction and the distance or displacement was in the 90-degree, the perpendicular direction. I have not changed the energy at all. What about the situation in which I threw the hammer? Am I doing work on it? Well, in order to throw the hammer, I need to exert a force this direction on the hammer, and I'm displacing it in the same direction. So in this case, I'm not changing the hammer's potential energy like I did when I lifted it up. I'm changing its kinetic energy by applying a force and a distance in the same direction. So I'm doing work on the hammer by changing its kinetic energy.